Well, good morning, everyone. It is 10 o'clock, so we'll go ahead and kick off week 11 of Crop Hour. This is Water and Weather Week. I'm John McMain, and this week was co-organized by Laura Edwards, David Kringen, and myself. So today we have two esteemed guests, Dr. Todd Trooien from South Dakota State University and Dr. Tom Scherer from North Dakota State University. And we will be looking underground today. So two exciting topics: subsurface drip irrigation and sub-irrigation through subsurface drainage systems. And just a few housekeeping things. If you have questions or comments, you can use the chat, or if you have specific questions about the presentation, you can use the Q&A feature that's found at the bottom of your screen. And that way that enables me to kind of keep track of what's been answered and whatnot. We will have CCA credits for each half hour. So Dr. Trooien for the first half hour, Dr. Scherer for the second half hour, and information of how to get those CCA credits will be given at the end of each presentation during the Q&A. If you have more questions at the end of the hour, you can stay on and we can have a more dynamic discussion with audio enabled. So feel free to stick around at the end of the hour and ask questions and have open discussion with both Dr. Trooien and Dr. Scherer. So with that, I'm going to go ahead and introduce Dr. Trooien. So Dr. Trooien received a bachelor's and master's from South Dakota State University in the Agricultural and Biosystems Engineering Department here, my home department here, and a PhD from Colorado State University. He has held research positions with the USDA Agricultural Research Service and Kansas State University, and he's currently a professor and natural resource engineer in ABE at SDSU. He's been here for about 20 years, a little over 20 years now, and teaches primarily undergraduate and graduate courses, primarily related to water issues for agriculture, and agricultural and biosystems engineering, ag systems technology, and precision agriculture. And his research is focused on irrigation, especially subsurface drip irrigation and animal wastewater use for crop production. And I would say Dr. Trooien is one of the definitely the regional experts and national and globally an expert in the area of subsurface drip irrigation. So we're very fortunate to have him presenting today. So with that, Todd, if you want to take it away.
Thank you very much, John. Thank you for that very kind introduction. Very nice. I appreciate that. I'm going to share some slides here, so some prompts to work from, and we'll talk about subsurface drip irrigation, SDI. And I'm going to say, if you have questions as we go through this, go ahead and use the Q&A to pop your question in, and we can address them as we go then, or absolutely save them till later if you wish to. But if anything pressing that comes up that I don't address right away, feel free to raise that Q&A flag. Okay, SDI and some contact information here. And actually, let's do that. There we go. So my email address is always a good way to get a hold of me. I want to acknowledge K-State. A lot of the images that you see here today came from K-State, and I'll show you that website actually before we're done. So what is SDI? SDI then is drip lines underground, right? Subsurface, buried in the root zone of a crop. And my starting point anyway is a geometry something like this, where we have drip lines spaced perhaps 60 inches apart, 5 feet apart, or that is between every other pair of crop rows, where the crop rows are spaced at 30 inches. And this is a standard system in the central and southern plains, and certainly is a good option for us here in the northern plains. So we bury those drip lines, maybe a foot, maybe 18 inches deep, anywhere in that range or even a little wider is appropriate. That can be changed or adjusted then based on operator preference, right? Do you want them a little deeper? Do you want them a little shallower for any of various reasons? If we look at a little bit of a three-dimensional view, we can see how that works out. Then every other pair of crop rows then is centered over a drip line. And so theoretically, then any plant is just 15 inches from the nearest drip line. And this works well for common soils, right? Silt loam soils, clay loam soils, even sandy loam soils. If we get into really sandy soils, then maybe we need to do things differently. And if you have specific operator preferences to do things differently, I know of a producer that actually has drip lines spaced 30 inches apart, and they're really happy with that system. So there are options and adjustments that can be made based on personal preference. So when we bury these drip lines in the soil, then in the root zone, we're depending on the soil to help move the water. And so here's an image from Northwest Kansas in a silt loam soil, and you can see how the water moves then away from that drip line, right? So it's moving laterally, it's moving upward, and certainly it's moving downward. And not surprisingly, more is moving downward as we can see, because gravity is helping it in that direction. But certainly water's moving sideways and upward too, and we depend on that then to move water from the drip lines to the crop roots. One other interesting thing about this image that I want to point out, this image was taken about 10 years or so after installation of the drip lines. And you can still see the shank mark there 10 years after installation. So that persists. And speaking of the shanks, then here's an image of a drip plow. Not the only drip plow in use, to be sure, and not the only design, but one good design. So for SDI, then we buy our drip lines then on rolls. Generally, we're talking about thin wall drip lines or drip tape. And so it lays flat on those rolls. We buy a roll, and that roll then is injected into the soil then at the trailing edge of the shank. So we can have multiple shanks then install up to maybe 4 or 5 drip lines at any one time. In this case, we're just installing 2 at once. And commonly, you know, with subsoiler shanks like this, takes about 50 horsepower or so per shank. So it's not an inconsiderable power requirement for this system. Okay. So a schematic then of what a system might look like here. And so all of this then is not unique to SDI, right? And that could be for any irrigation system, certainly a water supply, whether you're pumping groundwater or whatever your water supply is. And then various backflow prevention devices to protect our water supplies. May or may not have chemical tank and injector pump for center pivots or surface irrigation. Those are required in some form for SDI systems, as we'll talk about here in a couple of minutes. Filtration system, again, required for subsurface drip irrigation systems, may or may not be required for other irrigation systems. And then our field then with multiple laterals and distribution system to get the water to the crop root zone. So a quick note here about where does SDI fit? And traditionally, we would think that surface irrigated fields are a nice target for conversion to SDI because the topography is already set up nicely for SDI, generally flat or a small grade in one direction. So that's a good fit. But of course, not every field is flat enough to surface irrigate. So if it isn't, if there is some topography in the field, then what we usually need to do is use some PC or pressure compensating emitters. And that allows us to actually run the laterals up and down some topography. Now, we can't go up and down steep hills, really large hills, right? Because the hydraulics would result in non-uniformity of irrigation application. But if we use these pressure compensating emitters, then we can go up and down some hills. And indeed, we're seeing those PC emitters used in some of the systems here in South Dakota. PC emitters are probably a little more expensive and take a little more management, or you want to use a little more caution to keep them clean. But certainly they're being used and used well, and that's a good application of them. Okay, let's spend a few minutes here on why we would want to use subsurface drip irrigation and some of the advantages. And these first two here work together hand in hand, although they're not the same, but they work together in that this is probably the best way we know how to apply water uniformly to get to the crop ruts. All right, so and then not only is the water applied uniformly then, but any fertilizer that we inject, many forms of nitrogen are really nice to inject into these systems and use for irrigation then through the system. And then salinity can be managed well because we can manage the water well too, if salinity is a question in your area or for your system. Generally, we get good quality crops. In many places, we can see an increase of crop yield, fertilizer especially, but if we have some systemic pesticides or something we want to apply with the system, then again, that's applied uniformly because the water is applied uniformly. Water quality hazards, especially the runoff issue, where we can drastically reduce or eliminate runoff because we're not applying water at the soil surface anymore. We're applying it directly into the root zone. We can still cause nutrient leaching into groundwater if we're not managing a well-designed and a well-installed system, right? So we do have good control of the water, so we can avoid or reduce leaching, but we do have to use more caution to eliminate leaching. It's not as easy to eliminate as the runoff is here. Where we're wetting the soil surface less than with SDI, then we can reduce especially the germination. Generally, these are low pressure systems, so we can reduce energy costs, pumping costs mainly. If we keep the canopy drier, then maybe we can reduce some disease pressure, reducing humidities, improve cultural practices, and especially we can irrigate while we're doing cultural practices. And this is can be especially effective for alfalfa, right? So we can continue to irrigate as we cut and harvest alfalfa, and that can really kick the regrowth then into high gear if we can keep the water coming during that harvest time. Okay, whole nother page here of advantages, right? Because a lot of the system is buried, then we're less prone to be running things over. Excuse me. We're not sprinkling the surface again, so we can reduce some soil crusting if that's an issue. For some areas, double cropping might be an option. Fewer mechanized parts also plays into the ease of automation, right? Just in many cases, a relatively simple solenoid valve and a controller can automate these systems really nicely. A lot of the system is plastic, so we can reduce corrosion and which also relates then to use of degraded waters, especially things like animal wastewater, feedlot runoff, been successfully applied through SDI systems. Perhaps swine wastewater collected and then used through irrigation systems. Treated municipal wastewater is SDI used extensively in Israel for application of treated municipal wastewater. And especially high wind, but low temperatures then not an issue, so we can keep irrigating if that's an issue early and late in the season especially. And we can match the field sizes and shapes. We're not limited to a circle in the middle of a square, for example, for a center pivot. And we can space things to meet what we need, and these pressure compensating systems, then we can go up and down some slopes. And finally, maybe some germination possibilities, but this can be difficult. Okay, so got a quick question in here. Yes, root intrusion can be an issue. My understanding from the Central Plains, I'm sorry, the question is any problems with root intrusion using SDI with alfalfa? And I have not heard of specific reports of alfalfa root intrusion. There are some other crops that seem to be more prone to root intrusion, but this can be an issue with perennial crops, right? If the crop roots are growing for multiple seasons, they might grow into the drip lines. It hasn't been as much of a problem in alfalfa to my knowledge. Okay, so disadvantages. We'll just start with a whole list of them here, right here, rather than building the list. So expensive. They're expensive to install, maybe $1,500 to a couple $1,000 per acre, right? And again, can go up and down based on your system and your bells and whistles, but it's an investment. Secondly, then, worldwide, the main cause of loss of micro irrigation systems is emitter clogging. So we got to keep those emitters clean, and we'll step through a 5-step program here in a moment to see how we can do that. And then the next two, the maintenance and the visual indicators kind of work together. Because we can't see water coming out of a sprinkler nozzle anymore, we have to use indirect measures to make sure the system is running properly. Flow meters, pressure gauges at various places in the system. We got to use those to indicate performance, make sure things are working properly. We do have to do some filtration, and we may need to do more than that depending on the quality of our irrigation water. If we have some particular clogging hazards, we may need to do other things. We may need to inject inject something for pH control, for example. Because we're burying the system, subsurface repairs, got to do some digging. That's not inconsequential, especially where you have rodent problems, gophers, ground squirrels. They can cause great frustration, especially in the spring. We tend to see those kinds of damages during the off season over winter. So when you start the system again in the spring, you'll see leaks in the system where the gophers found it. And that can be frustrating. Design life might be shorter, shouldn't be, but may be cases. Because we're burying the system, then if we have errors in the design, it's tough to fix those. May require a whole lot of digging. Because we're wetting just a small part of the soil, then the plant rooting development might be affected. Again, light sandy soils, we need to be careful because we just get less movement through the soil in those sandy soils, less lateral and upward movement through the soil, should be clear. And we also might see some chimney effects. We need to have air vents and pressure release valves in the system to keep silt from coming back into the system when we shut it down. It's not portable. Systems can't be moved from field to field. So we need to want it in the system, in the field where we've got it. Tough for germination. Salinity could be an issue. Generally in the northern plains where we get some rain, we get help with salt leaching then from that rainfall. So it's not as big an issue as places that are really, really dry. Tillage options, we need to be careful we don't go too deep with tillage. Length of run may be limited, but we can overcome some of that with large diameter drip tapes. So we can go half a mile in many cases. There aren't as many systems out there, not as many learning opportunities. So it's a little less collective knowledge has been generated. What happens when the system is done? These systems should last a good many years, but not forever. What do we do with the plastic that's in the field then? Not as many systems around. There are turnkey systems available in South Dakota, so there are dealers working in this, just not as many. And again, as Tom asked earlier, pinching drip lines or root intrusion can be an issue in perennial crops, and then compaction can occur in some strange cases. So you see some benefits and some disadvantages. What we'll do here is, in my remaining time here, I want to step through this 5-step program for keeping those emitters clean. And here are those 5 steps then. Right. First of all, we select the proper emitters. And this is a compromise. We can get emitters in various flow rates, right? So larger flow rates mean larger holes, larger flow paths through that emitter. And then that's easier to keep clean. But if we use smaller emitters, generally we can reduce the cost and the complexity of our installed system because we need fewer zones. So there's our first compromise then is zone size and number versus emitter flow rates or emitter size. And we got to have proper filtration, and that may be as severe as the sand media filters are gold standard at this time. Or if you've got good clean groundwater, perhaps a really simple screen filter is adequate for your supply. The manufacturer of the drip line you select will have specific filtration requirements for their products, so you can get their requirements from the drip line company. And the dealers surely will know about that and be able to help you with that. We will have to do some chemical injection, and that may be as simple as setting up a chlorine injection once a year at the end of the year, just to clean things out a little bit if you have good clean groundwater. In this case, this image shows a research project in Kansas where we were pumping out of a livestock feedlot lagoon, and we actually were injecting chlorine and some acid here to control the pH to make the chlorine more effective. Right. So again, this will be based on your water quality, your water supply. Now, you can also use these injection facilities to apply fertilizers too. So that's one of the real benefits of SDI. Even though we're filtering that water, there's still smaller stuff that gets through, and we got to remove the stuff from the drip lines. Again, if you got clean groundwater, that may be once a year kind of an operation. At the end of the growing season, you open the flush valves and clean it out once. If you're pumping feedlot wastewater, then you'll do that more often. Here's a schematic of how a flush manifold might look, and you'd have multiple drip lines here feeding in and connected to reduce the valving requirement. Here's what it looked like at that feedlot site, actually, as the flushing was going on. You can see that the stuff is being removed from those drip lines there. It's a nice dark color. And then finally, we need to monitor the system to make sure that it's operating properly. And again, we can't see water coming out of sprinklers, anything. We have to use things like pressure gauges at various places in the system to make sure that our pressure and our flow rates are appropriate and are staying within our design guidelines, right? And so if we track those and measure pressure rates and, flow rates and pressures, then we can make sure that things are running properly and we're not generating or starting some clogging or have a leak somewhere. So there's the 5-step program then to keep those emitters clean and keep that irrigation system operating as designed and as installed for many years. Okay, I'll finish up here. SDI in the Great Plains is a website hosted by K-State. A lot of information here. And a lot of those images and drawings I actually retrieved from here. And they've got also an archive of reports and publications going back more than 20 years. So there's a wealth of knowledge here, and a shout out to Freddie Lamb for hosting this down at K-State. So there is the brief introduction to SDI and subsurface drip irrigation. And if we've got any questions now, or actually I'll hand this back to John on how you want to handle questions. And I sure appreciate your time and attentiveness here today. And I wish you all well. And if you got any questions, please do feel free to reach out.
Yeah, so thanks, Todd, very much. If anyone has any questions, feel free to put those in that Q&A feature, and I can direct those to Todd. Don't see any coming up immediately, but I did wonder, Todd, if you follow the 5-step program, what's kind of the ideal duration that you, or life that you would expect from a SDI system?
Yeah, great question. So a common lifespan might be 20 years for planning. The first research plots that went in Northwest Kansas went in 1989. They lasted 26 years, 27 growing seasons before they were just not performing as well and were replaced. So that 20-year lifespan target seems to be pretty reasonable. And certainly we've learned a lot since 1989 too, on those products.
Sure. So it really, I mean, if you think about the context of a farming operation that lasts as long or longer than a lot of typical systems and, you know, pieces of equipment and things like that. And so, you'd see similar thought going into the design and installation and maintenance, and you can get a similar return on investment. So here's a question. What would you say is the percentage of producers using subsurface drip irrigation versus traditional irrigation? This probably varies from place to place, but yeah, overall, what would you say in our area?
Very small, but non-zero. One in places where there has been some SDI development, the percentage are still generally in single digits in terms of SDI as a percentage of all irrigated acres. And certainly it would be small single digits here in the Northern Plains. But non-zero. There are systems, SDI systems operating successfully.
Sure. And I'm going to go ahead and throw the QR code. If you need CCA credits, you can scan this QR code and then get to another question here. So let's see here. Get the right screen.
Say, Todd, while John's doing that, any recommendation on drip tape comes in different mill thicknesses? Do you have any minimum requirement there or max?
That's that's a good question. Yeah, you can get various thicknesses. I do not have a recommendation or a guide for a minimum thickness at this point. That's a good question, though. It'd be a good question for your dealer and designer.
I think when I was in Arizona, the minimum we used was 10 mil, but in some cases they use 15 mil, which is a little more expensive, of course. It's thicker, but it's tougher.
Yeah, and going from surface drip to subsurface, because the subsurface drip lasts longer, generally that's a little thicker than the surface drip, right? Where they're planning on shorter lifespans, trying to use less plastic.
Excellent. And so if you haven't scanned the QR code, go ahead and do that. And we'll take one, I'll ask one more question, Todd, and then we'll move on into Tom's presentation. So in South Central South Dakota, we're far enough from the aquifer to access that. So our groundwater is very deep, 800 to 1200 feet, and isn't high quality. Is this something that can be treated through a system enough to use in subsurface drip?
Yeah, so that's a good question, and it would depend on the specific water quality issues. If it's just total salinity, that's difficult to treat in an economical way. If there are specific clogging concerns, then there are various water remediation things we can do. And again, I mentioned like an acid injection for pH control. Sometimes there might be an injection and settling requirement or injection and filtration requirement to get specific constituents to coagulate and then remove them from the water stream. But it really would depend on the specific water quality concerns.
But in general, there are ways that we can treat the water prior to
for some of those.
For some of those.
Just general salinity is tough to do in an economical way.
Sure.
We could do it, right? RO or distillation or something, but economics.
Excellent. Very good. So there's one more question in the Q&A. We can either, if you want to type the response, or we can catch that after at the end of the hour. And in interest of time, we'll move on to Tom, Dr. Scherer. So Dr. Tom Scherer is a associate professor and extension agricultural engineer at North Dakota State University, our neighbors to the north, and he is in their agricultural and biosystems engineering department there. He's originally from central Minnesota, raised on a dairy farm, served in the U.S. Navy from 1968 to 1974, and then has worked in University of Arizona, and then with NDSU since 1991. So he has extensive experience with irrigation, water quality, subsurface drainage in the upper Great Plains. And I have certainly appreciated his expertise and willingness to answer questions and let me come up to their workshops and things like that since I've been in South Dakota. So really appreciate him being in the region. And he's developed many educational aids, bulletins, circulars, demonstration units, performed over 300 irrigation pumping plant efficiency tests, and in general, very active on the extension and research front. And so, and I would consider Tom one of the leading experts on sub-irrigation, so irrigation through subsurface drainage systems. So we're very appreciative of his time and willingness to share his expertise today. So with that, Dr. Scherer, if you want to go ahead and take it away.
Thanks, John, for the nice introduction. I'm going to bring up my presentation. Can everybody see? Does that come through okay?
Yep, coming through great.
Okay, kind of like Todd, we have a number of people, you know, we've like South Dakota and southern Manitoba and western Minnesota over the last 15 to 20 years, a lot of subsurface tiling has put in because of the wet cycle. And along with that, because we're in that transition zone between dry and wet, we always get the question about, well, if I spent all that money putting in, is there a way that I can use it for irrigation? So title of my talk is Subsurface Irrigation through Tile on a Field Scale. You know, there really isn't a lot of research in this area. There's some in Ohio, and there were some done back in the 1980s in Michigan, but they were all pretty small plots. So I don't have a lot of research, so I'm going to be using some examples. But before I get going, you know, if you think about it, we're talking for the last 20 years, we've been talking about not just draining water, but sometimes controlling it, especially in this area. You're putting in a control structure like this with stop blocks where you can hold the water back after the crop is planted in spraying season and not let it leave. In a way, you're forming kind of a sub-irrigation by controlling the outlet. Along the same line, and this is, you know, our systems usually drain in May and June, and then dry up in July and August, and get to the point where we need water. So controlled drainage and sub-irrigation go together. So if you design for controlled drainage, then you can also use the system for sub-irrigation. So I'm not going to get into the design aspects, but I just wanted to point out that if you're going to do sub-irrigation, you gotta design for controlled drainage, and that's a whole different subject altogether. So just give you an idea, I keep running into people that have a misconception about tile. If you look at the two red line dots here, those are tile lines spaced a certain amount of distance apart. And typically when you get infiltration, water goes down, water flows out the tile and forms a mound between it, and then after the rain and infiltration stop, it recedes. So, and the typical flow pattern, which surprises a lot of people, is that water actually follows a path kind of like that to get to the tile. And so the water table has to rise to intersect the tile in order to flow out. But if we look at, if you're going to use this for sub-irrigation and you're putting water back into the tile, well, now you create the mound over the tile in between, and you got to put enough water in there to move the water laterally because you got roots down here that are using it. And so you kind of form a mound here between them, so that you get the water out here so the crops that are in between the tile can access it. And because crop water use in the summertime gets very great, the movement of water through the soil has to be faster than under drainage conditions. So the tile is under sub-irrigation has to be put closer together to make sure you get that water to flow across. Otherwise, you can end up with kind of variable growth. We saw that a few years ago on one field where the tile was spaced 60 feet apart, and the soybeans, you could almost see where the tile was because the soybeans responded. It was a dry year. So when we talk about sub-irrigation planning, the biggest problem that we have up here is finding a water source, because typically the areas that you drain are not typically over aquifers. They may be close to streams, but the stream may dry up in August, and you might have to have some kind of a capture pond with an alternate source of water. So what we found is, because we're tiling heavier soils in general, we got some people draining sands around Oaks area, but typically we need 2 to 6 acre inches per irrigated acre to get a yield bump enough to invest in the tile. So that doesn't sound like a lot, but if you think about it, if you got an 80 acre field, you need between 4 to 13 million gallons of water available in August, July and August, in order to take advantage and to be able to use it. In North Dakota, you need an irrigation permit if you irrigate more than 5 acres. I put that if needed because some areas you may not, some parts of the nation you may not need this. We found that our water commission, when they first applied for water permits for sub-irrigation, this was totally new to them and it kind of befuddled them for a while. And they debated whether they needed a permit or not. So anyway, I put that in there. Your state may require it. So give you some idea what some irrigators have done, and this has nothing to do with tile drainage, but these guys wanted to irrigate this area and there's no aquifers, but there is a flood control dam here. So they applied and they got a certain amount of water out of that. But to supplement their irrigation system, which are pivots, as you can see, they built this storage pond. And in the springtime, probably right about now, they're pumping, if the water's flowing in here, and they pump from here and they fill this up to store the water for later in the summer. And they've used this successfully for almost 20 years now. And to give you some idea, the footprint for this pond is a little over 6.5 acres. The amount of storage, the pond area itself is about 3.6 acres, and the water depth here in the middle is about 15 feet. So it stores about 45 acre-feet of water, which is enough to supplement what they get out of the flood control dam and in July and August. That doesn't mean that some years they aren't going to run out of water. We can get a drought and this will only take them so far, but they knew that when they built it. They were working the percentages. This is another one of their projects that actually, this field up here is tiled. They got one outlet coming in here, goes into this pond. They got another one here that goes in this pond. They got Willow Creek that runs here, and so they can tap into this to fill the pond in the spring. So they're basically, this is sandy soil, so they're recycling the tile water, and the topography allows them to do that. And they're very creative about this. And so that's what they had to do in order to get enough water to irrigate. And you can see this is their expansion area. This is courtesy of Bob Ibbotson up by Pembina, North Dakota. And he has several systems like this because there's no aquifer, so he has to catch spring runoff water. So if you're looking at planning, you look at the field topography, it's kind of like what Todd was talking about. The slope of the tile should be less than 0.5%, which is once you get above that, it's kind of hard to back water up and get water to flow, get it into the tile sufficiently. I'll show you that. And I have to throw this caveat in there that the field should require drainage because we've had some people put in tile in fields, they thought they had a high water table problem, but they never did. So, and this is hard information to find out, but that retarding layer, whatever causes the high water table, and that should be fairly parallel with the surface so that you don't end up with a whole bunch of water in one area and not in another. A lot of this kind of information comes from local knowledge. Somebody that knows the field, has farmed it for several years and has watched the water patterns and where they may and may not have got stuck. And then you determine, once you kind of work your field layout, you got tile spacing for sub-irrigation, and then you got to put a layout in there. And like I said, you need control structures to manage the water, and it'll become more evident here in a minute. But one of the nice tools that we use is the drainage calculator on the iGrow website. I use this in our tile drainage design workshops, and I know a lot of people, I just did a session on lift stations for tile drainage in Wisconsin and Illinois, and they use this quite a bit. Chris Hay did a tremendous job when he put this together, but if you notice down here, it'll calculate sub-irrigation spacing for you. And all of this part here is exactly the same as you would use for designing a drainage system. The only difference is you got to put in a design evapotranspiration rate of the crop. And I looked at the averages of a lot of our crops, our peak averages. And for North Dakota conditions, it's about 0.27 inches per day. That's the peak. And that would be a design point. That doesn't mean there isn't some days when it gets up to 0.35, but there's other days when it's only 0.15. So, but the average, and I've looked at many years, is around 0.27. So I stick that value in there, but you can put anything you want. And then the rest is pretty straightforward. And when you hit the calculate button, it would give you a spacing for you. And of course, the most important part of this is this KSAT value, how hard it is for water to move through the soil. The lower that value, the harder it is for water to move. So anyway, you have that resource available to you right there in the iGrow website. Very handy. I mean, it's got a lot of calculators on it. So there's two different ways you can sub-irrigate. One, you can back up, and this is the most common. This was researched pretty heavily in Michigan and Ohio and some other places. Basically, you got your main here and you got your laterals attached to it, and you pump into your control structure, and you back the water up, and it flows up and it goes up the pipes, and as it goes up, it seeps out into the soil. So that's one common method. And if you've ever driven up to the Red River Valley, we've got lift stations all over the place. If you happen to have a lift station, you can use it the same way by pumping water into it in the dry period and backing water up. The other method, and we have one cooperator here, he's on the Minnesota, about 17 miles from Fargo. He put in a drainage system with control structures, but he put a separate set of mains up here, and he pumps the water in here and lets it flow down, and then he controls the outlet here, so he can adjust his water flow here. And so that type of system, I couldn't find anybody else that had put it in. People have talked about it, but he put it in, and for 10 years now we've been kind of learning as we go. So is he. But he's put this on quite a few acres of his land now, so he's become quite familiar with how to use this practice. And he raises sugar beets on these, along with corn, soybeans, and wheat. So this is your typical lift station. This is one field that we've researched with my colleague, Dr. Gia. The main line runs along here, goes into the sump. You turn on the lift station, of course, you pump it out. When this farmer goes into sub-irrigation mode, he's got irrigation wells, and he pumps them into there and puts it in there and then backs the water up. And he's got a couple of wells that supply this. So that's the method he uses, and he's just using the sump here, and he's got a water level in here so it doesn't overflow on him. So I'm going to do this real quick. When he first put this system in, this field was tiled in 2003, and the southern half of the field was the problem area. So he didn't tile this half, but he tiled this half. And we started doing research out here in 2008 when I was in this mode. And of course, he has a lift station up here that goes into this county ditch. And then he drilled some wells up here and puts into the lift station and backed water up into here. So we found out from observation wells out here and all that the water, this is 2,000 feet, a little over 2,000. We could only back the water up 1,000 feet. None of the water got up here, even though the slope is 0.1% slope, or it's a 2-foot drop from here to there. It really only would back up about a foot, and of course it was flowing out. And that's what that's supposed to. So in 2011, and the spacing was 60 feet. So he changed it. He redid the field. He tiled him. He went to 30-foot spacing, which is for this soil is what was recommended. Then he split. He put a main here drill 2 more irrigation wells, put another sump pump in, and so he sub-irrigates this. He pumps water into this one and do this half, and then can pump into this one and do this half. And it's a small aquifer, so his total production is about 360 gallons a minute, with about 180 going to each one of these. Okay, that's the first example. Second example, this is the gentleman that put it in. He split his field. He put in 3 drainage mains here and split the field into, it's a 130-acre field, 150-acre chunk and 2 40s. And so he's got 3 control structures here that he can manage these different sections of the field. And to sub-irrigate it, he put in 3 mains here. This main supplies just this portion, this main supplies just this portion, and this main supplies this portion. And the way he's got a drainage ditch goes across the north side up here. It's kind of covered up, but this is a drainage ditch that goes back about 11 miles. So he's capturing water from other people and pumping it out. And he pumps out of here into a tank, fills that tank it's a 10,000 gallon tank, but he fills it about halfway so that he gets enough head to push the water kind of against the slope up those mains so he can control it. So he's got a submersible pump that he drops into there with a level control. If the water level gets too close, it shuts the pump off. And that has happened to him sometimes. And he was fully aware that he might run out of water, but he was willing to take the chance. And then he's got to come out of the tank. You can see goes into this manifold, and this goes to the 3 different mains. And those are his control structures. And these are his additions to them. He put floats in there with these can slide up and down, so he doesn't have to get out of his truck, walk down in there and measure the water level. He can see it directly by looking at these floating risers. Well, wait a minute. Sorry, let me back up. Now, in both of these systems, whether you backflow, and I'm going to go back up here, whether you feed it this way or you back the water up, what we found is you'd think with all the holes in the tile that the water going in here would seep out. But what we find is that water always takes the easiest path, and we end up the lower end of the field becomes pretty wet here. In fact, in this corner, one year in sugar beets, he had 10 acres of a root disease because of excess water that accumulated. Of course, this is the lowest part of the field. And so they really found out that you got to have observation wells out here sometimes to monitor these. And we had some for research, but they were up in this area, not down in here. And the ones where you back the water up, we found that this part of the field also gets wet. And the first example field actually had some drowned out areas because he was a little overzealous with running his irrigation system. So you got to fine tune that and really watch it carefully to make it work. The gentleman that runs this has now been doing it for almost 12 years, so he has a pretty good handle on how to manage his system. So I'm going to go to my third example. This is a nice sandy loam field. The problem is there's subsurface water coming from high ground to the east of here, flowing underground through here. And so this land, for many years, was in CRP because it was too wet to farm in the spring. And then later on in the year, it would dry up. And this farmer bought it and approached a tiler about tiling it so he could control the water, so he'd get in there and plant it in a timely manner in the spring. And this is just a an elevation shot across the north side of that field, and the outlet's over here. So he's got a nice gentle slope going this way. And so, and I'm sorry, this is just the soil that are in there. They're all pretty uniform, Uland sandy loam. But the contractor originally proposed just putting in a standard main and then going east to west and just tiling down the slope. But the farmer said, you know, this is sand, and in the future it could get dry, and there is a small aquifer under this area. So he got a hold of me, and I met with him and the contractor, and we said, well, let's look at some alternative designs. So what we did is we put the main down the north side, and then we put 4 control structures. This is the final design after a lot of discussion. And so there's about a 4-foot drop here. So every foot we got a control structure. So he can set these elevations in here all the way out to the outlet and control the water in this area. And he can also then monitor how much of this subsurface water is coming. So that's what the farmer did. And this is, you can see the hills in the back here. There's gravel pit up in here. So water flows here and then it moves downhill this way, and that's what kept his field wet. So his outlet's here, and he's got 4 control structures here. And last year I just walked out there and looked at it, and he does have these blocks set, and he's controlling the water. He hasn't drilled a well yet because he hasn't needed to, but he could either drill a well back here and pump into this one and then let it stair step down to the control it, or he could drill it up here and run a pipeline up there, whichever least expensive. But that's the third example of sub-irrigation, or people using control to hold water in the system. And then I've got this example, farmer up north central part of the state wanted to have sub-irrigation. He got a hold of Agram. That's a company, I think they're out of Illinois. And they designed him a system. And their system, the drainage lines are 15 feet apart. They're about 2.5 feet deep. And he ended up with 24 control structures in this field. And he made the investment. Like he told me, he says, it's not going to be paid for in my lifetime, but it will be in my son's. But anyway, so he had the system, and I couldn't get up there. I had conflicts when he was putting it in. He let me know, but I couldn't get up there because I had conflicts at the time. But in order to supply the water, he's got a drainage ditch that there's about 70 square miles upstream of this that comes out of the Turtle Mountain. So he's got usually a pretty good supply of water, and he can get water coming by even when it's dry at his place, because it may be raining up at what they call the Turtle Mountains, basically hills. But he dug a storage pond here to supply the water that he needed. He's got a pump, a VFD controlled pump, and these are all the manifolds going to different sections of his field. But he's got it set up so he can either pump out of the ditch directly, or he can pump out of the pond, or he can use the pump out of the ditch to fill the pond if he's not irrigating or doing it early. And gives you a better idea of the manifold that he put in. VFD controlled. When I was there, he was irrigating. This pump was only running at 41 hertz instead of the normal 60, and developing about 12 psi of head. So, at each of his outlets, he's got a control valve. So he found that he has to adjust these at different parts of the field, because some parts of the field take water more readily than other parts. So he's fine-tuned these, and usually once he gets them set, they stay that way when he starts sub-irrigating, unless he gets a big rain, and he has to go and pull these. But generally, it's not as much work as you would think. He only has to do it once or twice. And like I said, unless he gets a lot of rain and he has to go into drainage mode, then he just pulls this up and lets it drain. And he made his own valve adjustment. It's just PVC pipe that he puts over the top and adjusts it. And he's got metal covers over all of them so he can find them. He's seen some pretty good yield increase with this. So the last system I want to show you, and again, these are all farmer installed systems based on, I think all of these guys have been through our tile drainage design workshops, but in this field, he's got a low area here that's always wet. And then he's got an area up here that's wet in the spring, but it's a loamy fine sand up here. And then he's got a loams here, heavy loams. And so, and he's got a lift station here. So this is the west side of the field. This is the where the lift station is, and this is the drop in there. So you can see from here to here, there's a 10-foot drop up in this area, and then it just levels off. So you get water infiltrates up here, moves underground, collects down here. So his lift stations always seem to have water in it. So he and his sons designed this system where they tiled the whole field, and then up in this problem area, they went in between the tile and put in a separate system connected to this control structure. This one's tiled this way going down the hill, and this one's tiled this way going with the grain. And he's got a control structure, and he pumps out of here, puts it up here, and then he's got 2 diverter valves up here. I didn't put in all the lines here. This is all pattern tile down here. So he had to drill a well to help supplement, but it's a very small well. He's got 50 gallons a minute that he pumps in here. And you can see this is the low part of the field, and this is typically stays wet. In fact, there's kind of a wetland area right here and over here. And then this up at the top part of the field here is 2 diverters. The water comes in here, and he's got, this one is on, this one is off. And if you look inside, he just dumps in, and these are connected to his sub-irrigation system. He's seen a difference of between 50 and 80 bushels per acre on this field since he put this system in. He's really quite happy with it, and he's got another field nearby that he's putting in something similar to this. Again, using the existing topography and his knowledge of the field. And so out in the field, he's got a control structure. That's what he sets the level at on the one side of the field. So last 2 slides. If anybody is thinking of sub-irrigating, one of the things that we found out is that you can't take, you have to connect into your main. Well, let me back up. A typical drainage system, just used for drainage, typically is put in like this. The main is down here, and then a lot of the laterals, they start at a higher level, and then it bends down and it goes in usually at a 45-degree angle. Well, if you're putting water in here and trying to back it up, and these things are not usually, the level is not successive laterals can be at different heights, so you can end up with water going more into one than others. You have to, if you're going to sub-irrigate, you have to set up the main so that you drain this way so that the water can leave and go out. So your main has to be relatively shallow. And the other thing is where the laterals connect into the main, those connectors that are sold by the companies leak like sieves. So if everyone's got a leaky joint near here, then water, if you're trying to back water up this way, it just squirts out around there and you end up with some piping. So I know one manufacturer now sells one with a rubber sealant that you can get. The gentleman that we worked with that put in the sub-irrigation system, he actually used a foam. He foamed every one of these to seal them off so that none of them leaked. And if you're delivering water, like the one gentleman, this is his upstream This is supply line, the upstream side. And again, he sealed all that with foam, and then he set them all so that they're all, these lines could be at different levels in here because they wanted to equal amount of water going into every one of them. So there's some design requirements that you have to do. So just want to point out that if you ever, anybody is looking at sub-irrigation, this is an important point, is to make sure that your connections are such that you can get the water into the tile line uniformly all the way across. I think when you got 100 laterals, you got to make sure that the water is entering all of them equally. Otherwise, you end up with wet spots in the field. And we found that in some of these fields. So that kind of, John, that completes my presentation. More than willing to answer questions if I can.
Excellent. Thank you so much, Tom. I'm going to go ahead and get the QR code up here. So if anyone is needing that for CCA credits, you can look at that. And then, yes, if you have any questions, go ahead and put that in the Q&A. And then at this point, if you're interested in staying on to kind of have more discussion and a more dynamic Q&A, you can stay on, and then we will promote everyone to panelists that wants to stay on. So you can still use the Q&A if you want, or you can ask your question with a mic. So there is that CCA credit QR code. Go ahead and grab that if you need it. And I will stop sharing that now. And then again, go ahead and put some questions in the Q&A that you have. And then from now, we'll move into the, oh yes, and the survey. Yes, 2-question survey. Please go ahead and fill that out as well. And we will be sending out a survey towards the end of the week. So even if you don't attend the other crop hour talks this week, please be on the lookout for that you can have a little bit more detailed survey and let us know kind of what you think about this format and everything else. So this time, we will move into the discussion period. So again, if you